Hi guys, so let's get started with the week 9 assignment of VLSI Design Flow RTL to GDS the NPTEL course. So in this lecture, in this week, sir has mostly discussed about the power analysis and the various methodologies through which these can be detected. Okay, so let's get going with the first question, which is related to the statement about the power dissipation in a CMOS inverter. So first option is switching power dissipation occurs in the transistor when the input is fixed and the output rail to the output rail or the ground rail. See guys, switching, what does it switching mean? So switching basically means switching from 0 to 1 or 1 to 0, like a transition is happening. Then we say that switching is occur. But here it is saying that the input is fixed to the power rail, like input is fixed to VDD or input is fixed to ground. So if input is fixed, there is no switching, right? Switching means some transition is happening. So therefore, A option is not correct. The question is asking about which of the following statement about power dissipation in the CMOS inverter are true. Yeah, we have to select the true statement. So A is not true statement. Moving to the B option, short circuit power dissipation occur with a low resistance path that exists between the power and ground rail for the short duration of time. Yes, this is indeed a correct option. If you have studied the CMOS design, so CMOS is like this, right? This is PMOS. This is just a second. This is NMOS. This is NMOS, and they are connected to ground, and this is VDD. This is input. Here we are going to take output. Now suppose there is a transition of input is like this. So there is some reason where both this PMOS and NMOS both are on, and when the both are regions are on, then there is a low resistance path between VDD and ground, and this short circuit power dissipation will occur, and there will be a low resistance path for a short duration of time. So this B option is correct option. Third is static power dissipation occur in the output load capacitance when the inverter is toggling at a fixed frequency. So fixed dissipation occur in output load when the inverter is toggling at a fixed frequency. See, static power dissipation occurs when my input line is fixed. It may be fixed at VDD or it may be fixed at the ground, as it is as the power rail or the ground rail. But if it is toggling, then it is no longer a static power dissipation. Then it will be switching power dissipation, right? So therefore, the toggling should not be associated with static power dissipation. Static power dissipation, I will tell you, like if my input is a static input, like this is my CMOS inverter. If my input is static, suppose that my input is given to 5 volt, if input is given to like VDD, if it is static, then in this case what will happen, there will be some leakage static current that will follow, and the power dissipation due to this will be VDD into I leak, that will be the leakage current which can happen between the drain junction and the gate terminal of this MOSFETs. So these are some static current that can follow, that can lead to the power loss, static power loss. It is not related to the toggling. Okay, so this C option is also not correct. So we are left with only B option, and this question is asking about which of the statement is true. So only B option will be true. Okay. Now this is a good question. See here, let's try to understand what it is given here. Assume that the inverter drives a load capacitance of 0.1 femtofarad. Like, okay, so here we are given with load capacitance, this CL. CL is zero point 0.1 femtofarad. Okay, what is unit of femto? Femto means 10 raised to the power minus 15, and it is already 0.1 here. So it will be 10 raised to the power minus of 16 farad. This is my load capacitance here. Supply voltage is 1 volt, which means that VDD is 1 volt. Now assume that the inverter makes 1 into 10 raised to the power 9 0 to 1 transitions. Okay, so 0 to 1 transitions, how many transitions are like that? 10 raised to the power 9 transitions. And 1 to 0 transition are also 10 raised to the power 9. So total, now as we know that the capacitance, the energy stored in a capacitance is half 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 CV square. Like half CV square will be stored in 0 to 1 and 1, and that half CV square is going to get removed. So this 0 to 1 to 0, this will be treated as one complete cycle, right? So for that there will be how many transitions? There will be 2 into 10 to the power 9 transitions. That will be happening in 1 second. Okay. So so the power dissipations will be, so the power dissipations when charging and discharging the load capacitance will be CL into VDD square into alpha times of frequency of the clock. This alpha times of frequency of the clock is the activity that is happening in one time period. It is happening in one time period. Okay. So if you see that in 1 second, this 10 to the power 9 0 to 1, and in 1 second 10 to the power 9 1 to 0, both is happening. So there is total 10 to the 2 into 10 to the power 9 activities that are happening in 1 second. So it means that the power dissipated will become this CL, that is 10 raised to the power minus 16. VDD square is minus 16, VDD square is 1 square. Okay. And this alpha times FCLK is this much activity, 2 into 10 to the power 9. 2 into 10 to the power 9. Now let's match the units. So this has units of farad, right? This is farad, and here this one is actually VDD square, that is volt square. Okay. And here we have 2 into 10 to the power 9, that is transitions happening 1 second, so it is per second, right? Now if you see, that Q is equal to CV, right? Charge stored in capacitor is capacitance times voltage. So this F into V, okay, farad into voltage, this will become coulomb, and there is another voltage here, and there is per second also. So coulomb per second will become ampere, and this is ampere, and this is volt. So this is ampere into volt, this will become watt. So this will what not this is what is the like unit of power. So this will become 2 into 10 to the power minus 7 done. So it will become 2 into 10 to the power minus 7 watts. Okay. So this will be the correct answer, this one, 2 into 10 to the power minus 7 watt. Let's go to the third option, third question. Consider the following statement: clock gating technique stops necessary clock propagation to save power. Power gating technique reroutes data signal to save power. Dynamic voltage frequency scaling reduces clock frequency when possible to reduce dynamic power dissipation. Which of the following is true? Okay, we need to go to the true statement. So let me show you the reference which has been presented in the slides itself related to these techniques to reduce the power. Yeah, I think in this lecture, Sir has discussed this power gating is there. Hmm. Yeah, in the lecture number 30, guys, which is related to power optimization, we can see these techniques. So the first technique that is being discussed is dynamic voltage frequency scaling. So in this technique, as you can see, if there is some voltage, there is some task that is happening at some certain rate. If you reduce the supply voltage and the input frequency that is being discussed here, the topic, the thing that sir has taught here is like, if there is VDD is at a higher rate, VDD is something is higher, then CMOS will get a higher power, right? So it will do its activity faster also, like the charging of the load capacitance, it will become faster if VDD is higher. Now if we are reducing the VDD, then the charging of the load capacitance will become slower. So in that case we will require more time, require more than the usual time period to do the usual task. So our time period will increase and frequency will decrease. So that was the logic that was being discussed here. So that's happening in dynamic voltage frequency scaling. Okay, we, due to changing in voltage, we are also scaling the frequency. Like here, voltage becomes half, frequency also becomes half, and power dissipation becomes 1 by 8 times, and energy consumption become 1 by 4 times. Now, power gating uses the strategy of eliminating power supply. So, switch off the power supply of the block when it is not required. So, it happens that some part of the circuit are required to connect it to the power source only for a certain period of time when its computation is required. It is not necessary that for the entire process to be running, the switch need to be closed to for that path. Okay, so this power gating means we will eliminating the power supply whenever it is not required. And the next thing is clock gating. So clock gating is a technique in which we are enabling the flip-flops. We enable the flip-flops to catch the clock signal whenever it is required. It happens that the not every clock cycle requires the flip-flop to be engaged. So if there is some enable signal, that enable signal is connected to some combinational logic or some logic. If that condition is satisfied, then this enable is one, and if this enable is one, then only clock signal will reach to these flip-flops. So this technique is called clock gating. Okay. Now we are in a position to solve that question. Let's go to that question again. Okay, this was the question here. So what is written here? The clock gating techniques stops unnecessary clock propagation to save power. So yes, this is correct, right? This is a correct statement. Power gating reroutes data signal to save power. No. Power gating actually switches off, I mean disconnected our logic from the VDD, from the supply line whenever it is not required. It doesn't reroute the data. So this is not a correct one. And dynamic voltage frequency scaling, it reduces the clock frequency when possible. Yeah, this is correct. So option number A and C are correct. So this is the correct option here. Coming to the fourth one, consider the following statement. Short circuit power dissipation in a CMOS inverter increases when the slew of the input signal increases. Right, input slew. Okay, if input slew is increases, this is the slew, right? This is the slew. Like how gently or how fastly, how abruptly my input is changing, how my signal is transitioning. So if input is slew, it means that it will be a very gentle slope. Means from 0 to 1, it will rise very gently. So what will happen that the region where both the NMOS and PMOS will be on, this region will be higher. If this is higher, then in that case our CMOS logic will have a short circuit path following between the VDD to ground. Okay, due to this, a short circuit power dissipation of the CMOS inverter will increase. Okay, so this is a correct statement. Now, what is the statement B? It is given as static power dissipation in a CMOS inverter increases when the supply voltage increases. Yes, guys, as you know that this static power dissipation, this P static, what was that? It was VDD times of I leakage. So if VDD is how much? VDD is what? VDD is supply voltage itself. Now if you see, this is product of these two. If VDD is increasing, this P static will also increase, right? It means that the static power consumption of CMOS inverter will also increase. So this is also correct statement. Going to the third one, static power dissipation in a CMOS inverter increases when the time period of input switching increases. So if you see, if you increase the time period, it means that frequency of the clock will decrease. If frequency of clock will decrease, then what is switching power? Switching power is CL VDD square times activity, alpha times of FCLK, clock frequency. Now if you are reducing this term, this whole term will be reduced. So switching power will definitely decrease, right? So if we increase the time period, our switching power will decrease, but here it is saying that it will increase, so it is not a correct option. It means that we are left with option number A and B, which are correct. So yeah, this option is correct, only A and B. Okay, going to the fifth question. Consider a 6-input NOR gate. How many single structed faults are possible for this NOR gate? Fine. NOR gates, how many? 6 input. 1, 2, 3, 4, 5, 6. 6 input NOR gate. Okay, this is like this. So there are how many pins associated with this NOR gate? These are 1, 2, 3, 4, 5, 6, 6 for the input and 1 for the output. So there are 14 pins. Okay. Sorry. There are total 7 pins, in which 6 is input pin and 1 is output pin. Now, each of the input pin can be dealt with one of the faults. Like it can be either stuck at 0, or it can be either stuck at 1, right? This is also can be stuck at 0, stuck at 1, stuck at 0, stuck at 1, stuck at 0, stuck at 1, stuck at 0, stuck at 1. So like this bubble is showing my stuck at 0, and this closed bubble or filled bubble, this is called stuck at 1. in my diagram, 0 or 1. This is also 0 or 1. So each of the pin can have this two fault that can be stuck at 0, stuck at 1. So this 6 pin can have this 12 faults. This one pin, output pin, will have two faults. So there will be total of 14, 14 stuck at fault in my diagram. Okay. So in general, if there is a logic gate or any circuit which have n input pins and there is one output pin, so total there are how many? N plus 1 pins. Each pin can be stuck at 0 or stuck at 1. So total there will be twice of n plus 1 stuck at faults, right? Right. So you apply this here, you will get 14. What is the minimum number of test vectors for the 5 input NAND gate that can detect all possible single stuck at faults? Let's see this question. Try to understand this one. Minimum number of test vector for the 5 input NAND gate. Okay, I will try to explain this. 1, 2, 3, 4, 5. This is stuck at 0, this is stuck at 1, this is stuck at 0, stuck at 1, this is stuck at 0, stuck at 1, stuck at 0, stuck at 1, stuck at 0, stuck at 1, stuck at 0, stuck at 1. Now see here guys, if I want to detect my output, let me give the pin names first. A, B, C, D, E, F. Now if I want to detect my output F, if my output F is suppose stuck at 0. If my output is stuck at 0, this is 0. Okay, this dot is 0 and this filled bubble is 1, denoting stuck at 1. So if my out of this, let's not call it F, I'm calling it G. Fine. Because F sometimes represent fault also. So I'm not calling F as a pin name, I'm giving the pin name as A, B, C, D, E for the input pin and G is the output pin. Now if this output pin G is stuck at 0, it means that to get a different output when the fault is not present, I need to drive 1 here, right? Now to drive 1 here, what we require, if any of the input is 0, if any input is 0, it means that I will be able to drive 1 in my output, and in this way my stuck at 0 fault can be detected. Understood? So it means that if any of the input is stuck at 0, we will be able to detect if my output is stuck at if any of the input if any of the input is 0, we are able to detect my input, this output line is stuck at 0 or not, because we will be able to drive 1 here. That will be opposite to what stuck at 0 fault is giving. So it means that this A stuck at 0 will be able to detect this scenario, G stuck at 0. Okay, so G stuck at 0 is detected by any of the input is at 0. Any of the input, like let's say A is at 0, this will be able to detect these things. Now if G is stuck at 1, it means that I need to drive 0 here to get an output which is different from the stuck at fault. To get 0, what we need all of the input to be 1. We need all of the input to be 1, like this one, this one, this one, all need to be 1. So these stuck and fault, this fault model are like, how many this fault model are equivalent to this. This thing is as good as all these models stuck at 1. This G stuck at 1 means drive 0, which is as good as all these pins are stuck at 1. Understood? So it means that we are left with these 6 cases. Which 6 cases? A stuck at 0 and A stuck at 1, and then B stuck at 1, C stuck at 1, D stuck at 1, and E stuck at 1. Okay, so only these 6 faults will be able to detect all the possible cases. Now if A is stuck at 0, what is the test vector that we need to give here? We need to give 1 1 1 1 1 as the test vector. Why I am giving it 1? I am giving it 1 to sensitize this input. Sensitizing means to give an input which is different from this stuck at fault. Okay, so if this is stuck at 0, I am giving it as 1, and all other input are need to be given as 1, so that this fault can be propagated throughout this NAND gate. Guys, this is an important topic which is called as fault detection and analysis. If you want, I can dedicate a separate video for this topic. But for this video point of view, let's try to understand. For more detail, if you want, you can comment down. I can come with more examples for these kind of question. It will help you develop an approach to solve these kind of problems. So for A stuck at 0, the test vector is 1 1 1 1 1. If A is stuck at 1, it means I have to sensitize this with a value which is different than 1. What will be it? It will be 0. And all other input will be 1 1 1 1. For if B is stuck at 1, then the test vector will be this will be 1 0 1 1 1. If C is stuck at 0, it will be 1 1 0 1 1. If D is stuck at 1, then the test vector will be 1 1 1 0 1. If E is stuck at 1, the test vector will be 1 1 1 1 0. So these are the six test vectors that are possible to catch all the things, because there were six structured faults, unique structured faults actually. These are this that can be, that is equivalent to detecting to all other the faults. There are total six. This is the answer. Six test vectors. In the scan design, the scan cells get organized as a shift register in which of the following mode. So let's give you a quick recap of what sir has told us in that lecture of scan method. So actually there are the modes which are present. First, like test mode and the normal mode. Okay, one was normal mode and one was test mode. Okay, in normal mode, this test vector or this test enable value, it will be 0. And in test mode, what will happen? This test enable value will be on. Now, in test mode, there are two other cases. First case is if I what was the first case? Let me recall that. The first case is here shift mode. In the test mode itself, there is shift mode, and another mode is this capture mode. Okay. So in shift mode, what happens is that we shift the data through the scan cells or through the scan cells or of the scan chain, and the shift mode will happen when this scan enable bit is made 1. Scan enable is 1, and the capture mode is happen when test enable is 1 but scan enable is 0. Scan enable, we are going to just capture the output from the output pins. Shift mode, we are going to give the test vectors so that each intermediate pins of the circuit which contains of flip-flops and combinational logic can get initialized. So here it is, the question is asking about the scan cells get organized as a shift register in which of the following mode. So it is the shift mode, right? Through this flow diagram, through this branch diagram, you are able to see this is the shift mode. Going to the eighth question, consider the following statement about the scan design methodology. We have to select the correct one. Okay, let's go through the each statement. Replacing a D flip-flop with a scan cell can increase the overall area because a scan cell is larger than D flip-flop. Yeah, that is a correct statement, because what happens in a scan cell, we have a D flip-flop and apart from that, we have a mux here also. Mux is also there, and mux pin is connected to this scan input. Sorry, scan enable pin, and one is scan input and one other is normal D input. Okay, when scan enable is 1, then this scan input will be fed to this input of the D flip flop, right? So obviously you can see that it has a scan cell has a bigger area because it contains one mux, additional mux apart from a normal D flip flop. So replacing a D flip flop with a scan cell can increase the overall area because scan cell is larger. Yeah, this is correct statement. Replacing a D flip flop with a scan cell can increase the setup slack time of some timing path due to the D pin, because scan cells have extra delay of the multiplexer on the D pin pathing. Okay. Replacing a D flip-flop with scan cell can increase setup slack of the some timing path of the pin because scan cells have extra delay of the multiplexer. Correct, correct. Because the D pin have some extra this has this extra multiplexer path delay, due to which what will happen is that this is suppose a slack time, this is the required time, and this is the arrival time. Now, due to this additional path of mux delay, additional delay due to this mux in my path, what will happen? This arrival time will become arrive signal which was arriving earlier. It will arrive later on, right? Now, if the signal is arriving, suppose at 100 picosecond, now it will arrive at suppose it will arrive at 200 picosecond. Now, this suppose the required time is 300 picosecond. So earlier my slack was 300 minus 100, that was 200 picosecond. But due to this introduction of scan cells, it can happen is that my arrival time will become will be increased because of the delay due to this muxes, and this arrival time now become 100 picosecond, right? So you can see this arrival time is as 200 picosecond due to that slack, that is required time and its arrival time, that is the setup slack, has now reduced, right? So this is the question is saying that setup slack of the timing path of the scan cell due to extra what is written here? Replacing D flip-flop with a scan cell can increase the setup slack. No, 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 no. It will decrease the setup slack time, right? Because arrival time is going to increase. So B is not a correct statement. So A is correct, B is not correct. Okay, and third C is the purpose of replacing a flip-flop with a scan cell is to improve the controllability and observability. Yeah, that's the whole motive of giving the scan cell. Because through the scan cell, we are able to initialize the initialize the intermediate pins, or I can say intermediate pins, and the output produced by the intermediate inputs. Through those intermediate pins. I mean the logic gates which are in between of the flip flops, in beneath the inside of the logic circuit. So those output can also be propagated through this scan cells, right? So it will help in controllability, controlling the inputs of the intermediate logic gates, and observability. Getting these outputs done to propagate till the primary outputs. Yeah, both these purposes are solved. So A and C is the correct option here. Going to the ninth one. The non-linear power model of technology library typically models the internal power of an inverter as a function which are the following quantities. So if you remember the non-linear power model, it actually deals with this input transition which is slew, and second one is the load that load that my circuit is driving, load that my input is going to drive. Okay, capacitive load at the output of the given input. So it is A and B only A and B. It does not depend on the clock frequency. Okay. Non-linear power model, let me give you the reference also where it is. I remember it was there in one of the slides. Right. Here if you see, in non-linear power model, the input power dissipation depends on the input load and output slew. Sorry, output load and output slew. Output load means output net capacitance, or this input net radiation means input slew. Okay, so these two things are being discussed in this, and it will make a two-dimensional table, two-dimensional array kind of thing, which will be this is the input transition time slew, and this will be the output capacitance. The unit will be picofarad. Let's go to the question then. So it does not depend on the clock frequency, but it depends on the slew of the input and the capacitive load at the output. So A and B are the correct options. The 10th one, assume that you are running an OpenSTA tool to compute. Okay, these are some things related to OpenSTA tool. They are asking about which one is correct. So guys, in this case, OpenSTA tool get information from the synopsis design consent.hdc file. This is a correct statement. And it obtains information of the leakage power from the library file. Yeah, this is also correct statement. And it computes the power dissipated with cell using the power model. Yeah, power model is there in the library, like non-linear power model, NLPM, that we have discussed. This is also correct, which means that all of these options are correct. All of these options are correct. So this ends our video, and we have discussed all the questions that was in the week ninth, I guess, right? This was the week ninth assignment 9. So if you have any doubt, feel free to ask in the comment box. I will try to get back with the solutions. Thank you all.